Alright, here we go for sample test 4 for physics 234. So we have we're looking, find each of the following. Average acceleration, angular acceleration for a car that goes from rest to 40 meters per second around a corner of radius 50 meters in 7 seconds. Alright, so average angular acceleration, just like regular acceleration, we have the equation that is the change in velocity, but this time angular velocity divided by time. And so, but we have 40 meters per second, which is not angular velocity, it's v. And so, but we have the equation that v is equal to omega r, so omega is v over r. And so we can get, it starts at rest. So omega naught is 0. So we're going to have omega minus omega naught over the change in time, which they gave us to be 7 seconds. So that one is good. So we need omega, which is just v over r. We've got r is 50 meters. And so omega is v, which is 40 meters per second, divided by 50 meters, which is r. And so we've got 0.8 per second. And so radians is a strange character. It's kind of a unitless thing, but we use it as radians per second when we're talking about angular type things. And so let's put those in. So it's 0.8 minus 0 over 7. Oops. .8 divided by 7. Here we go. So we get 0.114 radians per second. Okay. Next problem. Angular velocity of a 0.5 diameter wheel on which a rock on the outer tread is moving 5 meters per second. Alright, so we're going to kind of assume that this is just a spinning thing. Yeah, so it's meant to be a simple problem, just a spinning thing. So the wheel is just moving, and it has a certain angular velocity omega, and then it's got a rock that is just moving at 5 meters per second tangentially on the outside. Alright, and so this is very much the same as what we just did. Omega equals v over r, and so it's 5 over 0.5 meters. The radius was 0.5 over 2. Alright, so 5 divided by 2.5 is going to be a 2. So it's 2 radians per second. Did I lose something? Oh, it was 0.5, sorry. 5 divided by 0.25 is 20. Yes. Okay. Letter C. The torque on a lug nut if a 10 Newton force is applied at a 75-degree angle to a wrench that is 75 centimeters long. So we got torque equals R cross F as a general formula. Most of the time we're going to use RF sine theta, or R, the component of F that's perpendicular to R. Let's just kind of draw a picture here. So we've got a wrench on a nut. We've got the length here is 0.75 meters, and we've got a force that's at 75 degrees on the wrench. Alright, so the force is going to have the y component. We'll call this one y, and it has an x component. The x component, depending on which way, anyway, is not contributing to the torque, right? It's just pushing in on the nut or out on the nut, not causing a rotation. So Fy is one that's causing a rotation. We got 75 degrees in here. Alright, and so Fy, so the torque is going to be R times Fy Fy is f hypotenuse and sine theta. So we can write f sine 75 degrees. In this case, the theta is the theta of this equation. So we've got r is 0.75 meters, f is 10 newtons, and then sine 75 degrees. So 0.75 times 10 sine of 75. We plug all that in, we get 7.24 Newton meters. Alrighty. Find the angular acceleration of a flat disc frisbee of radius 10 centimeters, mass 0.25 kilograms, thrown with a torque of 5 Newton meters. So we've got just a flat disc. Assume it's rotating about its center, right? And it's going to have a torque applied, and we'll assume it's a tangential kind of maximum torque kind of idea here. So when you throw a frisbee like that, we're asked for alpha. We have another equation for torque, Newton's second law kind of equation. The torque equals I alpha. And so we can get alpha as torque over inertia. Inertia for a disk, 1/2 mr squared. Alright, so that's going to be 0.5 times m was 0.25 kilograms, and then r was 10 centimeters, so 0.10 squared. Alright, so I is 0.5 times 0.25 times 0.1 squared. 0.00125 kilogram meter squared. Alright, the torque is given as 5, so that's easy enough. 0.00125 or 1.25 10 to negative 3 kilogram meter squared. So alpha then is 4. What happened? Shouldn't be 4 times 10 to the third. Ha! Okay, 4,000. Radians per second squared. If we got everything else in the right units, it looks like we do. Alrighty. Part E. Find the torque from a force of 5I3J2K with a moment arm of R is 1I minus 4J. So going back to the foundational torque equation, it is a vector, and it's R cross F. Alright, and we're going to have to use the actual cross product since we've got the vector notation. I guess it's possible to find the angle in between these two and their magnitudes, but it is a bit difficult. Alright, and so let's just use the cross product idea. So this one would be Rx, and this would be Ry, and this would be Rz, and I'm sorry, Fx. This is F. And then this is Rx and Ry. Rz is not existing, so it's 0. Okay, so when we got the cross product, you can do it different ways. Some people do it as a determinant of a matrix. There are lots of ways to remember. It's kind of goes around in a circle, kind of a pattern. So for example, for I, okay, so let's just gonna put, you're gonna have RF minus an RF in all of these. All right, but which one? So for the I, it's only the perpendicular part. So the X pieces do not appear. It's only the Y and the Z, and we go in order. So Y, Z for the starting point, and then Z, Y. Okay, for J, same thing. The Y components don't appear, just the Z and the X. So Z, X, X, Z. And for the K component, which is the Z, it's only the X and the Y. y, and the x. Alright, so let's plug in all that stuff. So ry is 4 times fz, which is 0, minus rz. Oops, I did that wrong. Did it backwards. I keep calling them the wrong things. So, oh, ry, fz is not 0. Fz is 2. Fz is 2, yes. Minus rz, which is the 0, times fy, which is 3. That gets multiplied by an I hat. And then we go to rz, which is the 0, times whatever, we don't care. And then rx, which is 5, times rx, which is 1. Why is he having trouble today? Rx, which is 1, times fz, which is 2. All that gets multiplied by j hat. And then finally rx, which is 1, times fy, which is 3, minus ry, which is negative 4, and fx, which is 5. And that gets multiplied by a k hat. Alrighty. So plugging in here, we get 8i, because that one goes away. Here we have 2j, and here we have 20 plus 3, so 23k. Alright. Last time I had a negative 23, but it doesn't look like. Rx is 1, fy is 3. Yeah, I think that's good. And that is Newton meters for the torque. Remember, torque is a vector. You want magnitude and direction usually. Usually we're looking at the magnitudes of the numbers, which would be the sum of the square root of the sum of the squares of this. We could get a magnitude. But in 3D, it's a lot more difficult to figure out angles and such, so that's good to just leave it like this. So we have it as a vector. We have magnitudes and directions, or components and their component directions. All right, let's look at F. Let's find the inertia of a golf club with a 0.25 kilogram head, the end of a 1 meter long 0.1 kilogram shaft. So we got a golf club of some sort. It's 1 meter long. The head is 0.25 kilograms. The shaft itself is 0.1 kilograms. And about the grip end, so this would be the grip end, so we're just looking at the axis is here. So we want the inertia of this guy when it's rotating. So it's kind of a system of two things. We've got a long thin rod, which is the shaft, and then we've got the head, which we're just going to call point mass. Alright, so for a thin rod about its end, we have the equation 1/3 ml squared, and for a point mass, it's always mr squared. So 1/3, this is the rod, so you need its mass, 0.1 kilograms, and the length is the whole length of the whole rod, so that's 1 meter squared. And this, so this would be m of the shaft, and this would be m of the head. Alright, and so for the head, we've got 0.25 kilograms, and the distance from the axis is r. For these point masses, it's always the distance from the rotation point, and so again, that's 1. Alright, so we're going to end up with 0.1 times 1/3, 0.1 times 1/3 plus 0.25. 0.2833333. 0.283 equals I system, or I club, whole golf club. Units, kilogram meters squared. Run out of room here. Let's look at the next one here. Find each of the following. Instantaneous linear speed of a piece of gum stuck to the bottom of a tire that is rotating, has a radius, and the car is driving down the road. Alright, so this one is a little different than what I assumed on the previous one, because now we're going to have the car is driving down the road and the tire is rolling on the road. Alright, going down the road. So the car has a velocity of some sort. And the tire has a radius of 0.25 meters. Alright, so this is, we can just treat it as basically as kind of a conceptual question. So remember when we talked about in class, once a tire is, or a wheel or something is rolling, the velocity at this very bottom point is 0. It's not sliding. Remember, we use static friction because it's just sitting down. It's sitting. So the velocity equals 0 at the bottom of the tire. Right? Now, same question, but now we're at the top of the tire. And so, I don't know if you remember from class, but the velocity we talked about at the top of the tire is 2 times. Okay, let's start. So the velocity of the center of mass is omega r, and we cut out quite often just write v is omega r. But that, when we write that, we mean the velocity of the center of mass of the thing. Right? So the center of the tire is going at a certain speed. We calculate that that's the speed of the car, right? 20 times the 0.25, so 5 meters per second. But, or let's just go ahead and calculate. So that's 20 radians per second times 0.25 meters, and so that's 5 meters per second. But the top of the wheel is going faster, right? Because the bottom of the wheel is 0, the top is going twice as fast. So v top is going to be 2 times v center of mass, which is going to be 10 meters per second. All right, so different points on the wheel are going different velocities. Of course, different radius. If it has a different radius, it's going different velocities. But it just by the, I guess, the physics of the problem. Okay, part C. Find the angular momentum of a 3 gram r equals 3 centimeter CD spinning at 600 RPM. So angular momentum, that's what we're calling L. It's the dual of linear momentum P. Remember, P is mv. So L is I omega, because I, inertia, is the dual of mass in the linear world, and omega is angular velocity, whereas v is regular velocity. So hopefully that helps you remember it. So we're given 600 RPM. That's an omega kind of number. It's a rotating speed, but it's in the wrong units. It's revolutions per minute. And we want radians per second, so we got 1 revolution, 2 pi radians, and 1 minute, 60 seconds to get to the right units. So omega is 600 times 2 times pi divided by 60. Yes, 20 pi, but what's the number? All right, 62.83 radians per second. All right, so we got omega. Now we need I. This again is just a disk. Use the disk formula. So I disk, just a flat cylinder, short flat cylinder thing, and 1/2 mr squared. 0.5 times m is 0.003, and r is 0.03 squared. All right, so the inertia is 0.5 times 0.003 little, 1.35 10 to the negative 6 kilogram meter squared. So the angular momentum then, 1.35 10 to the negative 6 times our omega, 62.83. These are all incorrect units, kilogram meter squared, radians per second. And so we got that answer times 62.83. 84.8 times 10 to the negative 6 kilogram meter squared per second. Lovely units, but it works. Yep. Okay. Next problem. Find the average angular velocity of a car wheel that does 10 revolutions in 5 seconds. So 10 revolutions, so we're looking for omega average. Angular velocity is omega. We're given revolutions, so that's kind of how many, it's kind of an angular distance, right? So we're going to use the delta theta over delta time kind of equation. All right, so 10 revolutions, how many radians is that? 10 revolutions, just multiply by 1 revolution. Well, put the revolution on the bottom and 2 pi radians because we're wanting theta in radians. So it's going to be 20 pi radians. So theta, or we can kind of really think of this as delta or whatever. Theta final is 62.83. Seems like we just had that number. So we've got theta minus theta initial, which is 0 over delta t. So we're just going to have 62.83 divided by the 5 seconds. So we're going to have radians per second. 12.57, or let's just go with 12.6 radians per second is omega average. Okay, kind of messy here. Part E, find the impulse needed to cause a 5 kilogram cart going 2 meters per second to speed up to 5 meters per second. Okay. Impulse. Impulse is the letter J, and it's just the change in momentum. So we're back in the linear. This is should be a small lowercase p. Change in momentum. All right. So we want to know. Change momentum is just mv. So we're going to have m, which is not going to change. M times v final minus m times v initial. Right. Momentum is mv. So we're going to have final minus initial to get the change. And we just got everything, I guess. So that's going to be m times v final minus v initial, which is 5 kilograms times 5 meters per second minus 2 meters per second. So pretty much 15 kilogram meters per second is the impulse. All right, and technically it's a vector, so we should say in the direction of motion. Kind of thing. All right, or we're kind of getting the direction from the sign of the thing. Part F, average force needed to cause a cart go, that should be a 2. Cart to increase its speed from 2 meters, so same thing, in 3 seconds. All right, so we're looking for now the force, whereas before we were looking for the impulse. So we have the equation that the force is the change in p over change in time, or it's j over the change in time. F is dp dt kind of thing we had. And so we're just going to use the impulse from above because it's the same conditions. and divide by the time, 3 seconds. And so we're going to have 5 kilogram meters per second squared, which is newtons. And it's an average force over the whole time period, so it might not be the instantaneous, or maybe at one point it's the instantaneous, but it's the average. Okay, that's what we were looking for. Part G. Find the torque on a shoulder joint by holding up, caused by holding up your hand 20-degree angle to vertical if your arm has a mass of 2.5 and its center is 0.5 from the shoulder. All right, so we're going to have think of our arm as just a thin rod. We've got an mg acting on it. The shoulder joint is the axis. Okay. And we got an angle 20 degrees in here. And we just want to know the torque at the shoulder caused by that mass. All right. So torque equals R cross F, or RF sine theta. R in this case is, we're given the center of mass. So we're assuming that the mass of the thing always acts at its center of mass. So the distance R is the distance to the center of the mass. So that's the 0.5 meters. F is mg, 2.5 times 9.81. And then we need the component that's perpendicular. We'll call it Fy, I guess. So let's just double check that that is the one. My drawings are a little off, but if this angle is 20 degrees, then also this angle is 20 degrees. All right, and so this component is associated with sine, so that is correct. So Fy is F sine 20 degrees. So this is F, so we need just sine 20 degrees added in here. All right, so the torque, and it is a vector. The torque is counterclockwise, or is clockwise. Let's get the number there. 0.5 times 2.5 times 9.81 times sine of 20. 4.19 Newton meters clockwise. All right. It's a little different than what I got last time. I'm not sure why. Looks good though. Okay. Next question. Find the speed of a 100-kilogram car that was going 10 meters per second and then was rear-ended by a 5,000-kilogram truck going 40 meters per second. Assume the truck's speed is 35 meters per second after this inelastic collision. So we're not, inelastic means kinetic energy is not conserved. So we're just going to have conservation of momentum. We don't have any talk about friction or outside forces, so we're going to just go with conservation of momentum. All right, so we're going to have m car v car initial plus m truck v truck initial is going to be equal to m car v car final, m truck v truck final. Okay, so we got 1,000-kilogram car going 10 plus a 5,000-kilogram truck going 40 is going to be a 1,000-kilogram car going what we're looking for, V car final, plus a 5,000-kilogram truck going 35. All right, all these are kilograms and meters per second, so all the correct units. So we can just solve this for V car final. It's going to be, bring this to the other side. So we've got 10 or 1,000 times 10 plus 5,000 times 40 minus 5,000 times 35. All of that divided by 1,000. Alright, something's not right. $35 sounds like a better number. So V car final 35 meters per second. Alright. Next one. Find the speed of a 5 kilogram bowling ball initially at rest after being hit by a 6 kilogram bowling ball going 10 meters per second and completely elastic. Alright, so this one we're given less information. We don't know any of the final speeds. But we are given that it's elastic collision, so that gives us another equation, namely that kinetic energy is conserved. So 1/2 mv squared of both balls on each side are equal to each other. Alright, so let's write some equations. So first, conservation of momentum. Just write conservation of P. Says, let's just kind of write it with the numbers in it. So 5, well, that's not, M5 times V5 initial plus M6 V6 initial equals M5 V5 final plus M6 V6 final. Alright, and so we're going to get 5 times 0, first ball is initially at rest, plus 6 times 10, yes, equals 5 times V5 final plus 6 times V6 final. Okay, so we don't know either one of those yet, but we have one equation, two unknowns. We can rearrange this. This is going to be 60. Which one do we want to solve for? Let's do it the same as I did it before. Let's solve for V, call it V6 final. So V6 final, the velocity of the 6 kilogram ball in the final condition. Just rearranging this, we're going to have 60 minus 5V5 final divided by 6. Alright, so that's about all we can do with that. Now we need another equation. So let's use conservation of energy, kinetic energy to be specific. And so we've got 1/2 M5V5 initial squared plus 1/2 M6V6 initial squared. Kinetic energy initially has to be equal to kinetic energy finally. 1/2 M5V5 final squared plus 1/2 M6V6 final squared. Kind of getting close here. Alright, so let's put in the numbers. Well, let's cancel out all these halves. Right, let's put in the numbers we know. So we've got M5, of course, is 5. V5 initial was 0. Plus M6 is 6. V6 initial was 10. Is going to equal to 5 V5 final squared, we don't know, plus 6 V6 final squared, again we don't know. That one. Okay, so we're going to end up with 600 equals 5 times v5 final squared plus 6 times v6 final squared. Let's substitute in what we know v6 final squared is in terms of v5 final squared, or anyway, in terms of each other. So we got 60 minus 5 v5 final divided by 6 squared. Kind of yucky. Okay, let's do some algebra. I wish I had more room. My fat marker here. So 600 equals v5 final squared. If we, let's going to take the squared out of there and make these inside squared. So this is going to be a 36 down here, and the top is going to have a b squared. So these two are going to just make a 1/6 on the outside. Okay, I lost my 5 there. Come back 5 plus 1/6 of squaring this polynomial. We're going to get 60 squared. 60 squared minus, so it's a minus b, so a squared minus 2ab plus b squared. So 2ab minus 2 times 5 times 60 times v5f, and then plus b squared. So it's going to be 25 v5f squared. It still has that 1/6 multiplier there. So 1/6 60 squared divided by 6 is 600. Okay. So we got 600 over here, but 5v5f squared, but this becomes another 600, so those are going to cancel out. And then we need 1/6 of this. We got 1/6 of 60 is 10 times 10, so it looks like minus 100 v5f. And then we've got 25 over 6. Oh, come on. Plus 4.167 v5f squared. Oh, I need more paper. Okay, so like I said, the 600s cancel. So we're going to have a v5f everywhere. So we can, realizing that the solution could be v5f being 0, which is the boring case of what we started with when it wasn't even moving. And so we're going to ignore that solution. We're going to go for the other solution. And so you can think of dividing out the v5f's. And so what do we end up with? Let's bring this 100 to the other side. So we're going to have 100 equals 5, so 9.167 v5f. And so we're going to have to steal some space from this problem. So v5f is 9.167 over 100. Which is, over 100. So, I don't know, 0.0917 meters per second. Which is not what I got before. but we'll go with it. And what are we asked for? Find the speed. Okay, so that's what we're asked for, the speed of the 5-kilogram bowling ball. Do your algebra, check that. Check my algebra, see if I made a mistake there. Last time I got 10.9 meters per second, which seems unreasonable. Okay, we'll go with this one. Because how could it be going faster than the previous one? So we'll see. This one seems awfully small. The other one seemed too big. Okay, let's go on. Assume a plank has a fulcrum 4 meters from one end, 20 kilogram mass on the same end. Alright, we got a complicated situation here. We need to draw the picture for. We got a plank. It's a uniform plank. It's 10 meters long, so if we go to 5 meters, we're going to put the plank's weight in the center. Remember, something has a center of mass. Something is uniform, then its weight is going to be acting at the center of mass. So we can go ahead and do that for the free body diagram. It has a fulcrum 4 meters from one end. Let's just put the fulcrum here. So this distance then is 1 meter. It's 4 meters from this end. A 20 kilogram mass at the same end. So we got another mass here. 20 kilograms times G, I guess, for its force at the same end as the fulcrum. 10 kilogram mass at the other end. 10 kilogram times G mass over here. And so its arm is going to be 6 meters. Okay. Assume a person adds force 2 meters from the fulcrum on the 20 kilogram mass's side to balance the plank. Alright, so, and we're going to assume positive direction for torque is counterclockwise. Let's just do X and Y. I'm sorry, X and Y as normal X and Y. Alright, person's force. So the question is, which direction does the person have to push? Let's say the person is pushing down. F person. What could go wrong? What could go wrong? We get a negative sign, and then it means that the person's actually pushing up. So, and that person is 2 meters from the fulcrum, so 2 meters from there. Okay, I think we've got the free body diagram pretty well. I guess we should really draw this as the force of the fulcrum instead of the actual fulcrum point. So pretend like that's the tip of an arrow there to make it a free body diagram. Okay, what is the torque about the fulcrum? So the fulcrum is going to be the axis caused by the mass of the plank itself. So we're talking about mpg here. And so the torque, R cross F, RF sine theta. Okay, nice thing about these kind of flat plank problems is all thetas are 90 degrees. Implies all the sine thetas equals 1. Alright, so this is going to be 1. Okay, so we can just put in RF times 1. So what's R for this guy is just 1 meter. And F is mg, mpg times 1. So that's 1 times mass of the plank, 5 kilograms, G, normal G, and then the 1. Okay, so 5 times 9.81. So the torque is 49.05 Newton meters for the final for a working number for a final answer. 49.1 Newton meters. Torque of the plank itself. All these. but is it positive or negative? So the torque of the plank is going clockwise, so it's really a negative because it's going clockwise. All right. As we said, positive was counterclockwise. What torque must the person produce to balance the plank? All right, so we've kind of jumped all the way to finding the answer here. So we need some sort of equation to get this. We're going to say that the sum of the torques is equal to 0 because it's balancing, no motion. So we got torque equals 0, and we've got, it's difficult to see, but we've got the fulcrum has no torque because the moment arm is 0, right? So we've got 1, 2, 3, 4 torques. We've got the torque of the 20, the torque of the person, torque of the plank, and the torque of the 10. So we're going to, the sum of the torques is going to be the torque of the 20, torque of the person, the torque of the plank, and the torque of the 10. And that's all going to equal to 0. And we're asking for what the torque of the person is. So the torque of the person, well, we can solve this for that. So the torque of the 20 is going to be, they're all going to have theta equals 90, so it's just going to be R times F. So R of the 20, the fulcrum was 4 meters from the end, so this is 4 meters. So R of the 20 is 4. Meters times mg of the 20. So it's going to be m was 20 kilograms and g 9.81. Is that positive or negative? All right, so you got to get the direction. It's pushing down. The fulcrum is here. It's pushing down. It's trying to make a force going, or torque going counterclockwise, so it's positive. All right, let's just put a plus to remind ourselves. All right, torque of the person. The way we drew it, it's also, the force is going down, so it's also causing a positive torque. So let's just call it torque person. Everything will still be positive. Torque of the plank, we calculated already, negative 49.1, 49.05 for working. And then the torque of the 10 is going to be negative, because it's pushing down on this side of the axis, so it's trying to cause a clockwise rotation. Its moment arm 6. So 6 times the force, which is mg. So 6 times 10 times 9.81 equals 0. So the torque of the person, this is going to be clockwise or counterclockwise. Since we got all of our signs put in correctly, is going to be 49.05 plus 60 times 9.81, doing a little bit of math in my head here, minus 80 times 9.81. Bring that one to the other side. And so, what do we get? 40.05. Negative 147.2 meters. Does that agree with what I have here? Not at all. All right, what did I do? Forgot some G's. All right. I think I did it wrong before. So Torque of the person. Did I remember my G in here? Yes, I did. Okay. Got G, got G. Okay. I think this looks good. So we'll go with it. So we end up with a negative number. And so the torque is actually, the person actually needs to cause a clockwise torque. Okay, so let's go ahead and finish out here. So the torque of the person is, we can rewrite it 147 clockwise if we want to, or negative 147 counterclockwise, whichever way you want to write it. Okay, but getting the negative sign means we assumed the wrong direction. So I assumed he had to push down, but it really has to push up. Next question. What is the force needed to produce this torque? So torque, again, R cross F, but it's R, F, sine theta is 1. The person's moment arm was 2. So this is all person, person, person. So the force for the person is going to be torque over his moment arm, which is 147.2 divided by 2. Um, 73.6. And this is, actually I got a negative 73.6, but we're going to, according to the way I drew it, but we can also just write 73.6 up, or I guess we can do this. So either one we want to do is the force of the person. Just be clear on the direction. All right. If you're just using signs and you don't say up or down kind of thing, then your sign better agree with what you drew on the picture. All right. So I drew down. I got a negative sign, so that means up. Okay. Number 4, find the following. Angular acceleration of a top when a force of 5 newtons is applied by a string wrapped around the top where its radius is 1 centimeter. The inertia of the top is this. Okay, so we've got a top. We're kind of looking at the top of the top here. It's got a radius of 1 centimeter, 0.01 meters, and we're going to have a string that's going to be applying a force. It's going to be pulling on the side, so we're going to think of a force like that, and so it should be at a 90-degree angle. Things are nice. So this is 5 newtons. All right, so again, torque, RF sine theta, or R cross F, so RF sine theta. Sine theta is 1 because theta is 90 degrees, and so we're not looking for torque, but we need angular acceleration. So we're also going to use torque as I alpha. Again, these are all vector kind of things, but so we're going to get torque first, and then we're going to use this to get alpha. So alpha is going to be torque over inertia. And they gave us inertia, so that will be good. All right, so find the torque. So torque is just RF in this case, so it's 0.01. Yes, 0.01 meters times 5 newtons, so 0.05 Newton meters. 0.05. So alpha 0.05 divided by 5 times 10 to the negative 4. And we end up with 100. Radians per second squared is alpha. Okay. Find the kinetic energy of a basketball spinning 200 RPM. We have the inertia of the basketball given. So kinetic energy of a rotating thing, right? We used to have kinetic energy always 1/2 mv squared, but now we got rotating. This one has no, we're assuming it's spinning like on a finger, doesn't have any, the center is staying still. Center is not going one direction or another, so there's no velocity of the center of mass, so that's not got any kinetic energy. It's just from the I omega squared. All right, so it's 1/2 0.0503 omega. Omega is 200 revolutions per minute times 2 pi radians per revolution, and 1/60 minutes per second. All right, so 200 times 2 times pi divided by 60. So omega is 20.94 radians per second. So kinetic energy .0 joules. Okay. Find the kinetic energy of a 5 kilogram bowling ball rolling 4 meters per second with a radius of 10 centimeters. So this one is actually has a velocity of the center of mass is 4 meters per second. And so it's going to have both rolling and, well, rotational and translational kinetic energy. So we're going to have to use Ke 1/2 mv squared plus 1/2 I omega squared. Okay. They didn't give us I, so we need to get I. I of a solid sphere, ISS, is 2/5, I believe. mr squared. Let me double check. Two-fifths mr squared. So it's going to be 2/5 mass 5 kilograms r 10 centimeters 0.01 meters squared. So I for the bowling ball is 0.4 times 5 times 0.1 square. 0.020 kilogram meters squared. Alrighty, and we need omega also. So we have the formula V equals omega r, so omega equals V over r, where V is the velocity center of mass, we got that, 4 meters per second over 0.1 meters. So we got 40 radians per second. Okay, so we got all the pieces. So we got 1/2 of 5 times 4 squared plus 1/2 of 0.020 times 40 squared. .56 joules. I did not do well when I did this practice test last night. I think this is the right answer, but I don't agree with myself on the previous time I did this problem. So check the work there. Okay, on forward. Problem number 5. Assume a 7 kilogram bowling ball with a 12 centimeter diameter. I really should look up how heavy bowling balls are someday, but these are just made up numbers. But 12 centimeter diameter rolls down a ramp that is 1 meter high at the top. It's a pretty high ramp. So we got something along these lines, something rolling, ball rolling, and we got 1 meter, makes the numbers nice, and the ball is going to roll on down here. Okay, so looks like an energy kind of a problem since we've got heights. We aren't given too much information. It always feels like energy problems. You don't have enough information, but usually you can figure out quite a bit from the way the problem's set up. And I'm asking you questions about energy, so that's giving you a hint here. So potential energy at the top of the ramp. So PE at the top is just going to be potential energy. There's no springs, so all we got is gravity, so it's mgh. And the ball is 7 kilograms, 9.81 meters per second squared. And h is 1 meter. All right, so PE at the top. $68.67. Official answer, PE top, 68.8 joules. Okay, write an equation for the KE of the ball at the bottom of the ramp. All right, so we got up here, kinetic energy is 0. It's just sitting there. We're about to let it go, or we just let it go. It hasn't started moving yet. Down here, potential energy is 0, and it's all kinetic energy. So KE at the bottom. So it says write an equation, so we're going to be solving for stuff, right? Just like the previous problem, it's got rotational energy, kinetic energy from the omega squared, but it's also got translational because the center is moving. So it's got 1/2 mv squared plus 1/2 I omega squared. And that's probably good enough. We know we're going to have more stuff to do, so it might be good to go ahead and calculate I. Again, it's a cylinder, sphere. So 2/5 mr squared, 2/5 times 7 this time, times 0.06 r equals 0.12 meters over 2, 0.06 meters squared. So I 0.0101 okay, kilogram meter squared, just in case. And we can always use, just looking ahead, looking for angular velocity. So let's go ahead and say that v equals omega r. We're going to substitute that in here in a minute too. But okay, let's move on. What is the angular velocity of the ball at the bottom of the ramp? So let's go ahead and write out where we don't have friction. We're assuming everything is conserved. So we got PE top plus KE top equals PE bottom plus KE bottom. All right, kind of our basic stuff. We already talked about kinetic energy at the top. There's none. And potential energy at the bottom, we're saying if we call this PE equals 0 level, then which we did when we assumed 1 meter to get our mgh for the top, and this one is also 0. So the kinetic energy at the bottom is equal to the potential energy at the top, which we have that number. So we can say that our 68.76, so this is equal to our equation up here. All right, let's, I guess, go ahead and rewrite that with stuff put in. So it's 1/2 m omega r squared plus 1/2 I omega squared. Okay, so I think we have everything except for omega. So let's write in the numbers. So we got 0.5 m was 7 kilograms, and we got omega squared r squared. Right, so r squared is 0.06 squared, and that's got an omega squared factor. And then we got another 0.5 I 0.0101 and omega squared. All right, so we get, factor out the omega, take the square root. Omega is going to be this, going to divide through like we need to. Going to be the 68.76 divided by all this factoring stuff, 0.5 times 7 times 0.06 squared plus 0.5 times 0.0101. I think. Square root 68.76 divided by Got everything put in right. Parentheses and all. All right, 62.42 radians per second. So official answer, 62.4 radians per second. Oh, let's see. I agree with myself for once. Well, kind of. Alright, keep going. How much of the kinetic energy at the bottom of the ramp is from rotational motion? So that's the omega part. So KE rotational is just the 1/2 I omega squared, which is just 1/2 of 0.0101 times 62.42 squared. So KE rotational is 19.7 joules, according to my calculation. All right. What is the linear velocity at the bottom of the ramp? So we're assuming this is of the center of mass, the whole ball, and kind of as one thing. And so at the bottom of the ramp, so that's just V at the bottom. And we've got omega, so it's just going to be omega R. And so 62.42 times R, which is 0.06. .75 meters per second. Okay, and then F. If the ball stops rolling after 3 revolutions, if the ball stops after rolling for 3 revolutions after it reaches the bottom of the ramp, okay, what is the angular acceleration during that time period? Okay, so 3 revolutions, that's telling us an angle. Theta equals 3 revolutions times 2 pi radians per revolution. All right, so we got 6 pi radians. So theta, we got a theta, and alpha. So this looks like a kinematic kind of equation. Remember, we have from kinematics, we have omega squared minus omega naught squared. Just like we had before, v squared minus v naught squared is equal to 2, was 2a, so we got 2 alpha times delta x, which is now delta theta. Okay, so we've got velocity here when it gets to the end of the ramp. So that's going to be our 62.42 radians per second. And it says it stops, so that one's going to be 0. The ending one's going to be 0. We're looking for alpha, and we got theta here. I guess we can call this really delta theta from here to there. We don't know, what's the starting, what's the ending. That's all. We just got the change, so we'll go with delta theta is 6 pi. So I think we're good. So we've got negative 62.42 squared equals 2 alpha times 6 pi. And so alpha is negative 62.42 squared divided by 12 pi. Okay. .103 radians per second squared. I guess kind of an average, assuming it's a constant. And that's not what I got before. Because I used potential energy. I messed up before. Alright, I think that's a good answer. Might double check my math though. Alrighty, let's see what's next. Consider 3 40-kilogram children riding on the outer edge of a frictionless merry-go-round with a mass of 500 kilograms and a radius of 2 meters. All right, so we got a merry-go-round of some sort, and we got kids on the merry-go-round on the outside edge. Don't know how they're staying on, but they're on there. All right, each kid is 40 kilograms, and the merry-go-round is 500, radius 2. What is the inertia of the merry-go-round if it can be modeled as a disk? So just the merry-go-round, I disk, and 1/2 mr squared. We've used it several times, so that's going to be 0.5 times 500 kilograms, and then the radius is 2. All right, so we got 0.5 times 500 times 2 squared, 1,000. So this is merry-go-round, kilogram meters squared. Okay. Good. What is the combined inertia of the children and the merry-go-round? So now the combo is we're gonna treat the kids as point masses. All right, so I of a point mass is just mr squared, where r is just how far they are away from the axis of rotation, which we're going to take the center of the merry-go-round as the axis. All right, so we've got I combo is going to be I disk, and the kids are really all the same, right? They're probably in different positions, but they have the same radius and the same mass, and there are 3 of them. So we're just going to do 3 times mr squared, which is going to be 1,000 plus 3 times their mass is 40 kilograms and their radius is 2 meters squared, because it said they're on the outside edge of the thing. So 1,000 plus 3 times 40 times 2 squared, 1480. Alrighty, so we've got the inertia kind of everybody together. They're spinning at 3 radians per second, so they're giving us omega when a 30 kilogram child running 5 meters per second, tangential to the edge, so just running along the edge and jumps on the merry-go-round. What will be the final rotational speed of the merry-go-round? Alright, so this is a conservation of momentum kind of thing. We got a collision happening, but it's a rotational momentum that we're talking about, angular momentum. And so we're going to have L1 equals L2 basically, and so we're going to have before the kid jumps on, what is the rotational inertia, and then after. And so just before or at the point that they just make contact, it's going to be I combo times omega initial of the merry-go-round and kids, which we're given as 3, plus this third kid, there's another kid here that's running and going to jump on there. All right, and so he's going to have a tangential velocity kind of a thing, and so we can calculate his rotational, what should we call this? This is the 4th kid. The 4th kid times his inertia. So we're going to translate his linear motion into a rotational motion. All right, and that's going to be equal another I total, because we're going to have to add him on to this for its rotational inertia times the final speed of the thing that we're looking for. All right, so we got momentum before equals momentum after, angular momentum before equals angular momentum after. We need to figure out, we're given his speed as a linear speed, but we know we know V equals omega R, so omega equals V over R. In this case, we're given that it's 5 meters per second, and R is still the 2 meters of the merry-go-round, so omega 4 is 2.5 radians per second. Okay. I4, this kid is a little lighter. He's still point mass, so let's call him mr squared. So he's 30 kilograms times 2 squared. So 120 kilogram meters squared. Okay. I total is just going to be I combo plus this last kid plus I4. Okay, let's put in numbers. So I combo is 1480 times initial is 3 radians per second plus this kid's, we translated his translational velocity into a rotational, so it's 2.5 radians per second, and his 120 inertia, and then the total inertia 1480 plus 120 times omega final. Alright, so omega final is all this. 1480 times 3 plus 2.5 times 120 divided by 1480 plus 120. Let's do that. Let's get some parentheses. 1480 times 3 plus 2.5 times 120 divided by 1480 plus 120. So I get 2.96 radians per second. Okay, good. 2.963 if we want 4 sig figs. Okay. What is the velocity of the last child on the merry-go-round after he jumps on? Okay, so he was going 5, but now that he's on, what's his velocity? Well, we're going to do v times omega final times his radius, and we'll assume he's just on the outside edge still. So it's going to be 2.963 times 2. Be 4 final, I guess. 5.93 meters per second. So he actually speeds up because the merry-go-round was going faster. So he slowed the merry-go-round down and the merry-go-round sped up. All right. Part E. What are the kinetic energy values for the merry-go-round and children before and after the jump on? All right. So KE initial is what? Well, the merry-go-round is just rotating. It's not got any translational motion, so it's 1/2 I combo omega squared, initial maybe. And then the kid number 4 is 1/2 mv squared. Alright, so we got 0.5 times the combo inertia 1480 times the initial speed of those guys was 3. And then we got the kid, 0.5 times his 30 kilograms times his 5 meters per second squared. So KE initial, 0.5 times 1480 times 3 squared plus 0.5 times 30 times phi squared. So kinetic energy initially is 7035 joules. And then afterwards, kinetic energy final, everybody's all on, so it's just going to be I called it I total, and omega final squared. And so that's 0.5 times 1480 plus 120, and then omega final 2.963 squared. Seven 7023 joules. Which is different than the number I got last time, but maybe it looks like it's fine. Okay, not much difference. Hopefully you can see all those numbers. Okay. Number 7, consider a mailbox with the 300-gram hinged door that opens down. Assume the door itself is a thin rod rotating about an end for finding its inertia. The door has a knob. Consider point mass 30 centimeters from the bottom of the door. So let's look at it from a side view. And actually we're going to have it about straight up and down. So let's look at it partially open. Alright, so we've got this whole length is 0.4 meters, the big mailbox. Alright, we've got a knob on it that's 0.3 meters. We've got the hinge here, axis. And we've got 0.3 meters this distance. And so it's going to have its own mg, and then we're going to have an mg from the knob. Alright, we're going to have a force, call it Fx from the box itself and Fy from the box itself. Let's just take torque positive and counterclockwise as normal, and let's just do x and y as normal for now. Should be good. What is the combined inertia of the door and the knob? Alright, so I system, I guess, is going to be I of a thin rod. The thing of the door is a thin rod, because looking at the side view it looks like a rod. And for these twisting things, the depth of it doesn't really matter. It's kind of strange, but that's how it works. And then we're going to do I of the knob, which we're going to think of as a point mass. Alright, so that's going to be for a rod about its end, 1/3 ml squared, and for a point mass, mr squared. So that's 1/3, and this is mass of the, we just call it m, mass of the door, and this is mass of the knob. So we've got mass of the door, 300.3 kilograms, and the length is going to be how far. Remember this, this is the length. We're not doing the force, the torque yet. Okay, length is just the total length of the rod, which is 0.4 meters. And then mass of the knob, what's a heavy knob? 0.4 kilograms, and its distance from the axis is r is 0.3 meters. Alright, so I system 0.3 times 0.4 squared divided by 3 plus 0.4 times 0.3 squared. It translated what I wanted, I think. So it's 0.052 kilogram meter squared. Okay, that goes up there. If the door is released from rest when it is almost closed but makes a 10-degree angle with the vertical, so we're going to put in 10 degrees here, what will be the angular acceleration immediately afterwards? Alright, so we got something that's moving now. We want alpha. We're going to use Newton's second law, so we're going to do the sum of the torques about an axis is going to be I alpha. Alright, so before we've been doing some static problems and it was sum of the torques is equal to 0, but now we're moving, so we got alpha. Alright, what torques do we have? So we're going to pick the axis to be here, so that the forces of the mailbox holding the door up have 0 moment arms, so they don't have any torque. So we're just going to have torques from the knob and from the door itself, and we're just going to assume that the knob is connected to the door and acting right on the door. Okay, so let's sum up our torques. And unfortunately the angles are not 90 degrees, right? So we've got to find the piece of the torque, the piece of the mg. Let's blow this up a little bit. Alright, so both of them we're going to assume are acting, you know, they've got their mg's, they're straight down. We got 10 degrees in here. And what we want is the perpendicular part, right? We want this F perpendicular. Alright, so just looking at this setup, that's going to be the sine component. F perpendicular is going to be sine, right? So it's going to be mg sine 10 degrees for each of these two masses. And so we're going to have, for the door itself, we're going to have its moment arm. So remember, torque is, we're going to use RF sine theta, right? And for the mass of the door itself is just half the distance of the door. We're assuming it's a uniform nice thing, and so R of the door is going to be 1/2 of 0.4, 0.2 meters, right? And the knob we already said was at 0.3. So we're going to have these two, they're both going to be negative the way I said torque was. So we got negative moment arm for the door times the force of the door is mg. M is 0.3, 9.81, so this is mg, and then sine theta, sine 10 degrees. Alright, to get the component that's perpendicular. And then the knob, very similar, but its radius is 0.3 and its mass is 0.4, and its g is the same. 0.4 times 9.81, and then sine 10 degrees also. All that, let's just calculate that. So we're going to have 0.2 negative 306.6, 10 to the negative 3 meters. So anyway, negative 0.3066. No, I didn't calculate that. Okay. Equals I alpha. I we have from before, and so we're looking for alpha. So alpha equals the sum of the torques over I. So alpha equals negative 0.3066 over 0.052. $5.897. So officially, so we're going to put this up here. So alpha equals 5.9 radians per second squared. Okay, is that what I got? I don't know. Yes. Okay, part D. What is the tangential acceleration of the knob in this condition? Is it more or less than acceleration due to gravity? So is it more or less than g? All right, so a sub t is alpha r. Alpha is the same for all points, but the acceleration is different depending on how far you are from the axis, right? So alpha we just got is 5.897 radians per second squared, and then r of the knob, it was 0.3 meters from the axis, and so a sub t, take that last number times 0.3, 1.77 meters per second squared, and it is less than g. All right, less than 9.81, so. Which makes sense. In class, we did an example where it was more out, and we found that the acceleration at the end was more than g. But this one, it's pretty straight up. It doesn't have a lot of acceleration yet. So that's good. Last problem. Assume an arm holding a book shown. This is a picture from the other class's textbook, and we're going to take counterclockwise as positive. So draw a free body diagram for the horizontal part of the arm and the hand. So we've got, or think of it as a beam, or kind of a beam. We're given that the center of mass is over here for the arm, so it's not quite centered. The distance here is 16 centimeters, 0.16 meters. And then we've got a book that's out here at 0.38 meters. And it's got a weight, some weight of the book. Little b. We've got the bicep muscle pulling up here. Force of the bicep, we'll call it capital B. And we've got the force of the elbow. And they give us the picture FE, and I mean we could do the math, but looking at it we see that all the forces, there are no forces in the x direction. So if there potentially there could be a force of the elbow sideways, but there's no other sideways force. So if we sum the forces in the x direction, we'll just say f of x equals 0, or f sub e in the x direction is 0 because there are no others. So we just went ahead and gave it as the force on the elbow is just right there. Okay, and so we want positive torque is counterclockwise, and we'll just do regular x and y directions for this thing. I guess we can also make a note, all thetas are 90 degrees, so all sine thetas equals 1. Yay, because all the forces are perpendicular. They should be, they don't necessarily look like it, perpendicular to the beam. And the pivoting axis is the elbow here. Using the elbow as the pivoting axis, what is the torque caused by the book? All right, so the book is way out here. Again, torque is R cross F, which is RF sine theta. But sine thetas, we just said are 1, so it's just going to be R book, F book. We're given the mass of the book, so it's going to be R book, M book, G. And R of the book, 0.38 meters. Mass of the book is 4 kilograms. and G 9.81. So torque of the book, 0.38 times 4 times 9.81, 14.91 Newton meters. Officially, torque of the book, 14.9 Newton meters. I didn't think about the sign. Go back. It's causing a torque to make a clockwise rotation, so I need a negative sign on these guys. Okay. So that's a little hard to tell that it's a negative, but it's negative 14.9 meters. Or we could just say this, it is a clockwise rotation. So it tells you that it's clockwise. Okay. What is the torque about the same axis caused by the weight of the arm? Basically, same story, right? T arm, it's going to be R arm, force of the arm. Sine theta is again equal to 1. So it's just going to be radius of the arm, 0.16 meters. Force of the arm is mg of the arm, 2.5 kilograms times 9.81. Sine theta is still 1 for this case, so 0.16 times 2.5 times 9.81. So the torque of the arm, negative 3.924 with multiple sig digs, T arm 0.92. We can say clockwise. Okay. Just be clear, if you give it this, give it a sign, or you can say clockwise. Hopefully it's not confusing. What is the torque caused by the force at the elbow about the same axis? So the force at the elbow, Fe, but the axis is here. So Re equals 0. So the torque of the elbow equals 0. Torque of the force of the elbow equals 0. So it's equal to 0. Find the force required of the biceps muscle to hold the book steady. So we're looking for FB. Okay, so here's where we finally get to do some Newton stuff. We're going to do the sum of the torques equals I alpha, but it's going to be equal to 0 because we're balanced or steady. No motion. All right, no acceleration. Okay, so the torques are going to equal to 0. So what torques do we have? We have torque of the bicep, and we've got, I guess we just call them all positive for a moment. So torque of the arm and torque of the book. That's all we got, right? And that's going to be equal to 0. And so torque of the bicep is going to be, that's for the force. So force of the, it's R times F. So R the bicep times F of the bicep. And that one is actually causing a positive torque. Let's just put a plus there to remind us that we did check the sign. And then we got torque of the arm we already calculated. We need to keep the sign correct. 3.924. And of the book, 14.91 equals 0. R of the bicep is given 0.04 meters. Okay, so F, force of the bicep, then is going to be, bring those to the other side, 3.924 plus 14.91 divided by R of the bicep, 0.04. So we got the force. 3.924 plus 470.8 newtons. So officially 471 newtons up, according to the direction that we assumed. Okay. Find the force on the elbow. Yeah, we're going to run out of room. Okay. Well, maybe not. So summing the forces, like we said before, they kind of showed us that the sum of the forces of x's is going to say the force on the x component of the elbow force is 0. So we're just going to sum the forces in the y direction. And again, that has to be 0 because nothing is moving. And so that's going to say negative force of the elbow, it's going down, plus force of the bicep, which is going up, minus the weight of the arm, minus the weight of the book, equals 0. So the force of the elbow equals, bring that to the other side, force of the bicep minus the weight of the arm minus the weight of the book. We were calling that little b. And so we've got 470.8 minus, we didn't calculate those weights, so we've got m of the arm times g of the arm minus m of the book, g of the book. And so 470.8 minus 2.5 times 9.81 minus the book 4 times 9.81. And 7 newtons equals force of the elbow. All right, which is down. That's the direction we assumed, and we got a positive number, so that means it is down. All right, that should do it.